Think about the most advanced AI. It can write, create art, and solve complex problems. But what if it's not following a single command that a human actually programmed? The secret lies in a revolutionary process that allows a machine to teach itself. Welcome to the Deep Dive.
AI is pretty much everywhere now, isn't it? Like song recommendations, helping doctors, even those self-driving cars we hear about. But have you ever stopped to really think how these smart systems, well, how they actually learn? Today, we're diving into machine learning and neural networks. We want to cut through the buzzwords, really get to the core of how these things work and what their impact actually is. Our mission is basically to demystify how these digital brains get built and taught.
It really is a big shift from how we used to program computers, a fundamental change. Instead of us writing every single instruction, every rule, machine learning lets the computers learn directly from data. They essentially build their own internal program. We call it a model. It reminds me of what Arthur Samuel, a real pioneer, said way back in 1959. He described it as the field giving computers the ability to learn without being explicitly programmed. That's the key.
Okay, so they learn from data instead of rules, but how? Is there just one way they do this learning?
No, not at all. It's helpful to think of it in three main ways, three main paradigms. First up, there's supervised learning.
Supervised? Like having a supervisor, a teacher.
Exactly like that.
Mm-hmm.
You give the system data that's already labeled. So think about a spam filter. You feed it thousands, maybe millions of emails, and each one is already marked spam or not spam. It learns the patterns from those labels so it can then figure out new emails on its own.
Okay, that makes sense. What's next?
Then you've got unsupervised learning. Here there's no teacher, no labels. The system just gets raw data, and its job is to find, well, hidden structures or patterns all by itself.
So like finding groups of customers who behave similarly, maybe? Even if you didn't know those groups existed.
Precisely. Marketing segmentation is a classic example. It finds the clusters without being told what to look for. And the third one is reinforcement learning. This one's about learning through trial and error. It gets rewards for good actions and penalties for bad ones.
Ah, like training a dog almost.
Sort of, yeah. Think of a self-driving car, learning to navigate. Good move, positive feedback, bad turn, penalty. It constantly tries to maximize its reward, essentially learning by optimizing its behavior over time. It's like a digital toddler learning to walk, fall, get up, adjust, try again.
Okay, different strategies for learning. Supervised, unsupervised, reinforcement. Got it. But what's the actual machinery? What's going on inside that lets them process all this data?
Right, that's where artificial neural networks, or ANNs, come into the picture. Now, they're inspired by the structure of the human brain, but it's really important to stress they're not literal copies, not biological replicas. But a key principle does echo biology, the idea that neurons that fire together, wire together, connections strengthen with use.
So what are the building blocks? What's a neuron in this context?
A neuron in an ANN is actually a pretty simple computational unit. It takes inputs, and each input has a weight, like how important is this piece of information? It sums up these weighted inputs, adds something called a bias. Think of it as an adjustable starting point or threshold. And then, crucially, it passes this sum through an activation function.
Activation function, why is that so important?
That's the secret sauce. Without it, the network could only learn linear relationships, basically, draw straight lines through the data. The activation function introduces nonlinearity. That's what lets the network learn really complex, messy, real-world patterns, like recognizing faces or understanding language. It handles the curves, not just the lines.
If you're finding this deep dive valuable, take a moment to subscribe to make it make sense. New topics are broken down every week.
Okay, so you have these neurons doing calculations. How are they organized?
They're arranged in layers. You have an input layer where the raw data comes in. You have an output layer which gives you the final prediction or decision. And in between, you can have one or often many hidden layers. And these hidden layers are really where the deep in deep learning happens. They learn hierarchies of features starting simple, like edges or corners in an image, and building up to more complex concepts, like eyes, faces, or objects.
Okay. Networks built from layers of these neurons. So how do they actually learn from mistakes during training? How do they adjust those weights and biases you mentioned?
Yeah, that's the core of the training process, and it's iterative. It happens over and over. First, data flows through the network from input to output. That's called forward propagation. The network makes a prediction, basically an educated guess. Then we need to know how good or bad that guess was. A loss function calculates that. It quantifies the error, the difference between the network's prediction and the actual right answer.
And that error tells it how to get better.
Exactly. That error signal is fed backward through the network. This is the clever part. Backpropagation. Backpropagation efficiently figures out how much each weight and bias in the entire network contributed to that error. Then, using an algorithm, usually called gradient descent, the network adjusts those weights and biases slightly in the direction that reduces the error.
So it's like finding the steepest downhill path to lower the error.
That's a great analogy. Think of a mountain climber in the fog. They can't see the whole valley, but they can feel the slope right under their feet. Gradient descent is like taking a small step in the steepest downhill direction, hoping to eventually reach the bottom, the point of lowest error. It's this constant loop. Predict, measure error, adjust.
But does it always find the best path? Does it ever get stuck?
It can sometimes get stuck in local minima, not the absolute best solution. And another big challenge is overfitting. That's where the network gets too good at the training data. It basically memorizes the examples, including the noise, instead of learning the underlying general patterns. So it performs poorly on new, unseen data.
Right, memorizing the test instead of learning the subject.
Exactly. There are techniques to combat that, but it's a constant consideration.
It's amazing how these fundamental ideas have led to such specialized and powerful tools we see today. What about specific types of networks that have been game changers?
Oh, absolutely. Two huge ones come to mind. First, convolutional neural networks, or CNNs. They completely revolutionize computer vision, how machines see and interpret images. Think about detecting tumors in medical scans, or identifying pedestrians in cars for autonomous driving. CNNs are designed brilliantly for spatial data like images.
Okay, CNNs for vision. What else?
Then there are transformers. These really kicked off what people call the attention revolution, especially in language. Transformers are the architecture behind most of the large language models, or LLMs, like GPT that you hear about constantly now. They allow models to weigh the importance of different words in a sentence, no matter how far apart they are. That's key for understanding context, generating human-like text, and doing advanced machine translation.
Incredible power. And of course, with that kind of power comes, well, significant things to think about for society, right?
Absolutely. We have to talk about the ethical challenges. Algorithmic bias is a huge one. If the data used to train these models reflects societal biases, the AI will learn and often amplify those biases. We've seen this in facial recognition systems performing worse on certain demographics, or in hiring tools favoring certain groups.
And the black box problem, too. I hear that mentioned, not knowing why the AI made a certain decision.
Exactly. Especially with complex deep learning models, it can be incredibly difficult to trace the exact reasoning behind a specific output. This lack of transparency is a major issue, particularly in high-stakes areas like loan applications or medical diagnoses.
And what about jobs? The whole AI taking over narrative.
It's more nuanced than that, I think. Yes, AI will likely displace jobs that involve routine, predictable tasks. That seems unavoidable. But the flip side is augmentation. AI can also enhance human capabilities, automate the tedious parts of jobs, and free us up for more creative or strategic work. It could lead to increased productivity and potentially new kinds of jobs we haven't even conceived of yet. The key will be adapting, reskilling, and rethinking how we integrate AI into the workforce.
It's a complex picture. So looking ahead, this rapid push towards maybe artificial general intelligence or AGI AI that can learn and reason like a human across many domains, it raises some really profound questions for all of us, doesn't it? So maybe the question for you listening right now is this: what steps will you take to understand this technology better, to engage with how it's developing? How do we ensure that our wisdom in governing AI actually keeps pace with our incredible power to create it? Something to think about.
Thanks for joining our deep dive. If this sparked an idea for a future topic, let us know in the comments below. You can continue exploring this subject by watching our next video right here, or subscribe to catch all our future breakdowns. We'll see you in the next one.